It's good. It's good. So today we're going to be looking at derivatives of trig functions. So this was an observation that we made already earlier in a homework problem. If we look at f of x equals to sine x, and we look at all the place where we have like a horizontal tangent or a tangent that's positive 1 or negative 1, those seem to line up with the zero or the x-intercepts for the cosine function and the maxes and mins on the cosine function. And we might guess that the derivative of sine is cosine, right? This was something we did in a homework problem way back in chapter 2. How would we prove that the derivative of sine is cosine? We use the definition of the derivative. So we should say the limit as h approaches 0 of sine of x plus h minus sine of x over h. Again, that definition of a derivative is one of those things like we just expect you to have from here on out. We've done it a bunch of times. It's something we need to have memorized. All right, how are we going to cancel out that h out of the denominator? Because we need to kind of do that or somehow deal with it for us to be able to do this limit. Sine definitely doesn't distribute. None of the trig functions distribute. In fact, the only two operations you know that distribute is multiplication / division and the derivative operation. Those are the only two things that we have that distribute.
Can you do, sine x plus sine h, and then the sine x's cancel out?
Well, that's distributing.
Oh, that's just what you...
That's what Rita had suggested that I poo-pooed as a, no, we can never do that. But you're right, there is something we can do with this. Does this look familiar to you?
It's an identity.
That is an identity. That is an angle sum identity from trigonometry. I know. Who remembers what it is?
Is it 1? No. Is it 0?
It's sine, oops, don't forget the limit. Yeah, it's going to be sine x times cosine h plus sine h times cosine x minus sine x all over h. So yeah, that was a angle sum identity from trigonometry. So how's that going to help us? You can't add them together. Hi, Elena. On the Fritz?
Yeah.
Okay. All right. Well, this is what I would do. Notice that this term and this term both have a sine h in it, or a sine x in it, right?
Yeah.
So what I think I would do is I would break this into two fractions where one fraction has the sine x's in it and the other fraction has the cosine x in it. Is that okay? You see what I did? I just did some rearranging, right? And the reason I'm going to do that now, if I look at that first fraction, I have a greatest common factor there, right? So let's go ahead and do some factoring. So I'm going to use some limit laws here. So when I factor that sine x off, that's going to be its own limit. And that'll be its own limit. And I'm going to do the same thing over here, where I'm going to take the cosine x, and then I'm going to leave the sine h over h. Zoom that out a little bit so you can see it all at once. From factoring the sine x.
Oh.
See the blue highlight?
Yeah. Okay.
That's okay. Prater? Okay. Does that look familiar? I think when we went back to 2, we did that limit. So I'm just going to take advantage of that right now. So that takes care of that. The problem still left with us, though, is going to be this piece here, right? So let's see if we can figure out how to do that piece. Because if we can do that, then we can just start plugging in. Because if I do the limit as h approaches 0 of sine x, well, that's just going to be sine x. And the limit as h approaches 0 of cosine x is just going to be cosine x, right? Because there's no h's in them. What limit do you suppose that cosine h minus 1 over h is going to turn out to be? Good job, Emma. 0. Why? Because we're expecting the answer to just be cosine, right? All right. So let's take a look at that limit and see if we can figure out if that's 0 or not. Does cosine h minus 1 remind us of anything? It's not an identity, but it looks like half of it, like a conjugate of something, right? What would its conjugate pair be? Cosine h plus 1. And why am I interested in its conjugate? Yeah, because cosine squared minus 1 was one of those identities back from trig. So cosine squared h minus 1 is going to be close. I know 1 minus cosine squared is equal to sine squared. There you go. H over h. So that's going to be negative limit as h approaches 0 of sine h over h times limit as h approaches 0 of sine h, right? Well, this is 1. And what's sine of 0? 0. So what's this come out to be? 0, which is what we hoped it was going to happen, right? So this is 0. So we do end up with just cosine x. That was kind of a lousy proof because we had that extra limit in the middle there that we had to do, but what's the takeaway though for us? The derivative rule is? Yes, the derivative of sine x is cosine x. That's the takeaway. Would I ask you to do the proof again? No. Are we going to keep doing proofs in class during lecture? Yes, because odds are that eventually you get into a calculus class, if you're going to be taking more than one of them, where almost everything your professor's doing in class is going to be a proof, and then you have to deal with keeping up with that, so we're going to do a little bit of that still here. Okay? Sounds good. All right. So we did the proof there. We saw this. We proved that. And we have this, right? Right, we took the limit as theta approaches 0 of sine theta over theta to be 1 from 2.2. We looked at that already. We proved that the limit as theta approaches 0 of cosine theta minus 1 over theta is 0. We just did that. And we, with those two parts, we're able to show that the derivative of sine x is cosine x. So let's do an example. So let's say that we want to differentiate y equals x squared times sine x. How do I do that? Take the derivative. That's okay. Again, if the vocabulary, it takes some getting used to. If you're not sure on the vocab, like ask. It's important. Right? If you don't understand the direction, there's not a lot you can do. Very good. So Pierce identified that this is a product rule situation because we see we have one function x squared times another function sine x, and there's no way algebraically to combine the x's together. So it must be done using a product rule. So we're going to have, say that y prime is x squared times the derivative of sine x plus sine x times the derivative of x squared. The derivative of sine x is cosine x, and the derivative of x squared is 2x, and I'll write that in front because it feels like the more natural place to put it, and we're done. Well, is there any like terms to combine there? Any trig identity you could apply to make it simpler? No? That says that. That's it. Yep. That goes into your toolbox of rules, derivative rules. What if we wanted to do the derivative of cosine x is equal to negative sine x? How would I prove that? I use the definition of a derivative again, right? So we'd have the derivative of cosine x plus h minus derivative of cosine x over h. Do you really want to do this again? It's like the same thing, kind of, right? We'll just skip it. That's fine. But that's how you would do it. It just is tedious. What if I wanted to do the derivative of tangent and show that that's equal to secant squared? How would I do this? I would not.
Quotient rule.
Yes! How using the quotient rule?
I just know that's because of 1 over cosine. So I was thinking fractions. Yeah.
Well, what's tangent the same as?
Oh.
Oh.
So
Oh, so then
we can do the quotient rule. So the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. The derivative of sine is cosine. The derivative of cosine is negative sine. And if I look at that numerator, when I multiply it out, that's just 1. 1 over cosine squared is secant squared, and we're done. That was a little bit easier than having to use the definition of a derivative. Now, you could have done that, but wowzers, I bet it gets ugly. So the derivative of tan is negative sine x. Yeah, Emma? Cosine squared x plus sine squared x. That's what the numerator simplifies to. I just wrote it above it, rather than spending another line to rewrite everything again. You know what I mean? Okay. Now that we have the derivative rules for sine and cosine, I could use a similar process to figure out the derivative of cosecant, of secant, and of cotangent, right? Doing the same kind of processes, just using quotient rules. Let's not do that in practice. Let's just give it to you all at once. So here's your 6 trig derivatives condensed into one place. Typically, you wouldn't use a parenthesis or a prime symbol to do something like this. You'd use the ddx. If you had like y prime equals cosine, then you'd say that like y prime is like negative sine x. But you typically wouldn't use a prime on something like that. You'd use the ddx because it's really clear like what that is. And if you put a prime on there, it looks a lot like a power of 1, which gets really confusing. So the convention would be use the ddx notation there. But that, again, these are good questions to be asking, right? Like, how would I write this? Could I write it this way? You know, like, yeah, but I wouldn't, just because the odds are I'd go back and look at the prime and go, that's a 1. you know? Like, that's a Kulik mistake, for sure, where he misremembers what the heck he meant when he wrote something down. But there's only one thing that looks like ddx. There's no other symbol like that looks like that for me to get confused by it. So, all right, let's do another example. So it says, for what values of x does the graph of does f have a horizontal tangent when f of x is secant over 1 plus tangent, or secant x over 1 plus tangent x? First thing I'm going to need to do is take the derivative, and then once we have that, how are we going to find where the horizontal tangents are? What is the slope of a horizontal line? 0. So we'll set the derivative equal to 0 because the derivative gives us the slope of the function at any value x, right? So far, so good?
Yeah.
Okay. So to get that derivative, we need to use quotient rule. So it's top times the derivative of the bottom minus the bottom times the derivative of the top over the bottom squared. That's not right. What did I make? What mistake did I make? Yeah. And I flipped it, right? Well, so did I. I apologize. If you guys would have caught it quicker, would have saved everybody the aggravation.
I caught it by
Well, let's blame Rita then, everyone. If you think I've made a mistake, say something. Even if I haven't, I won't ever be mad that you're like, did you make a mistake there? And if it's like, no, I didn't make a mistake, and it's clear I didn't. I'm going to be mad at you for that. That's okay. It happens. All right. So let's see, where are we at now? The derivative of secant is?
Or secant x tan of x.
The derivative of 1 plus tangent x is going to be 0 plus secant squared x. And I am going to leave this as 1 plus tangent x. I don't see any benefit I'm going to gain by foiling this out at the moment. So rather than foiling it out, I'm just going to leave it the way it is. Is that okay with everybody? All right, let's take a look at that numerator. Now I could FOIL or multiply this stuff all out to start. But I notice here that I have a common factor. Probably going to pull that common factor and then multiply the remaining stuff together. Gut says that'll probably make life easier. The derivative of 1 is 0, and the derivative of tangent is secant squared.
Oh.
So I did that after I factored the secant x out. I went ahead and multiplied that rest of that stuff out. What do you guys see now? Can probably do better than this because I'm not looking forward to trying to solve something like that, right? That looks like a nightmare.
When you change the secant squared x back into tan x and like subtract it, like or like cancel, or like because like in the numerator there's tan of x would be minus tan of x.
In the numerator, you want to turn what into
like
what?
The secant squared x back into back into tan of x.
Yeah.
So you want to undo the derivative?
Yeah, because then it would be.
You can't undo a derivative when you've taken a derivative. But
Wait,
the bottom, like if you break the bottom, then cancel all the tan squared x.
so you can't do that because you can't cancel things that are being added inside of a fraction. You can't take the derivative again because we've already done the derivative part is done.
Is it a
So,
trig function?
yeah, it's going to be a trig identity. That's right, Pierce. Who remembers their basic trig identities?
Is it secant of x? Is it secant x?
Isn't it secant x? So let's put this back in here. So I know that,
No.
well, you should have said it louder so everybody would be sure they heard you.
I said it, she goes, no, we're not doing that.
Well, I think you're on the bottom. So did we get the sheet on our test by chance, or is this like a?
Elena, I have some bad news for you.
No, we're not that.
I can't remember all of these.
Yes, you can.
Well, the goal, the hope would have been that you remembered most of them from last year.
I
remember P1.
Good. If you remember P1, how do you get P3 out of that? Divide each piece by cosine squared. Sine squared over cosine squared is tangent. Cosine squared divided by cosine squared is 1. 1 divided by cosine squared is secant squared.
You know that.
So if you remember your like just the reciprocal and quotient identities and P1, which everybody remembers P1, you can get P2 and 3 for free, basically.
And then what about the co-functions? Do you think those are going to reoccur?
No.
Oh, no.
But the odd evens will.
Oh, no, that's easy.
Okay. All right. Let's go back to where we're at. Okay. So what did we do here?
We simplify the bottom.
I'm not going to FOIL the bottom out. I'm more interested in turning this into 1 plus tangent squared.
Then you separate.
And then I can cancel some tangent squareds.
That's crazy.
And that seems like a much better plan to me.
Yes.
Now, you could do that in the bottom, but I don't think it's going to get you where you want to be. The thing you have to be pretty careful about there is that you make sure you distribute the negative when you turn secant squared into 1 plus tangent squared. So I have secant x times tan x minus 1 over 1 plus tan x squared equal to 0. Now I feel good about solving this because that numerator now looks doable. So, what do I start by doing? Emma, what's up? Because the question asks us then, for what values of x does the graph have a horizontal tangent? That's why we're setting it equal to 0 now, because with horizontal tangent lines have 0 slopes. So f prime of x is our representation of slopes. We're trying to find where that's going to be 0. How do I solve this fraction equal to 0? When is a fraction equal to 0? When the numerator is 0. So I can just set the numerator to 0 and ignore the denominator for now. What do I still have to worry about the denominator for, though? I have to make sure any answer I get from the numerator doesn't give me also a 0 denominator. But I'm pretty sure that's not going to happen since I have a tan minus 1 in the numerator. I just have to make sure that the answer for the secant part. Everybody's okay there? Now, how do I solve something like this? You use the 0 product property since they're being multiplied together. So you can take each factor and set them equal to 0 separately. Where is secant x equal to 0? Incorrect. That has no solution to it. Why? Well, secant's the same as 1 over cosine, right? So this would be the same as cosine x equaling undefined. Right, when you do the reciprocal of both sides. And cosine x is never undefined. Emma's like, ugh, so mad at you right now. All right, let's do the other piece then, which is great because that was the piece that could possibly have given us a 0 denominator, right? Okay, so how do I solve tan x minus 1 equal to 0? Great, add 1 over. So tan inverse of 1, great, which is? Nope. 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 What? 45 degrees, but we're in calculus. Pi over 4. Yes, and every pi k units after. Where k is just some positive or some integer, right? So any positive or negative multiple of pi. Why is it pi and not 2 pi there? Do you remember that, Braden? So it's yeah, so typically the fundamental period of sine and cosine is 360 degrees or 2 pi. Tangent, though, which is what we're using here, has a fundamental period of pi or 180 degrees. So that's why it's pi instead of 2 pi there. So there's our answer. This was our derivative. So again, as a reminder, the AP does expect you to know the unit circle. I know. Should I put that in here at the same time? Might as well, right? Let's drop that in. I probably have that sitting here somewhere. That won't take too long to find. I think that's a chapter 2 thing.
I think at the end of chapter 5 basics, you just go back.
Oh yeah!
Right there.
It is down at the bottom of that sheet, isn't it? Thank you, Elena. That saves me like a whole bunch of looking. See, it's on the same page. Perfect. Okay. Let's do some more examples. Physics, anyone? An object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t equals 0. Its position at time t is given by s, which is equal to f of t, which is 4 times cosine t. Find the velocity and acceleration at time t and use them to analyze the motion of the spring. Okay, how do I find the velocity? Good, it's the derivative of position. So what's the derivative of 4 cosine t? Negative 4 sine t, right? Remember the coefficient rule for derivatives? We can just ignore that coefficient, take the derivative of the function part, and then just tack the coefficient back on, right? So negative sine was the derivative of cosine, so we just made it negative 4 sine t. Okay, how about acceleration? It's the derivative of position, or the second, or derivative of velocity, or the second derivative of position. So if I take the derivative of negative 4 sine t, what do I get? Negative 4 cosine t. Remember, the derivative of sine is positive cosine. Okay, so if we wanted to analyze the motion of the object, what could we say about this thing? Well, what's the maximum speed and maximum acceleration going to be? Or I should say velocity. So what did you say, Rita?
Negative 4 and 4.
So which we want max and mins. So the maximum should be, and the minimums would be negative 4, right? Okay. What is the, when the acceleration is at its maximum, when acceleration is at its maximum, what is the time? All right, let's do at its minimum. Let's start there. When is cosine t equal to 1? 0. Okay. What would the velocity be? Maybe let's just say when is acceleration going to be at its maximum then? Pi, right? At cosine of pi is -1. -1 times -4 is +4. At t equals pi, the velocity there again is 0, and the acceleration is 4. Where is velocity going to be at its minimum? Pi over 2, right? Sine of pi over 2 is 1. What's the acceleration there? 0, right? Cosine of pi over 2 is 0. Any guesses that this one has to be? I mean, come on, guys. 3 pi over 4, right? So I'd say that's probably good for analyzing its motion, right? When the thing is accelerating the fastest or slowest, the velocity is then at 0, right? Which probably makes sense. What's happening when the velocity is at 0? If it's something bouncing on a spring, it's like at the bottom of the spring or at the top of the spring, or the top of its bounce or bottom of its bounce, right? That should make sense to me. And when the acceleration is 0, the velocity is at its fastest, so it's probably like right as it's passing like its stationary position, like if you just let the thing dangle.
Like how do you put pi?
The which pi? This one?
Yeah, that.
So cosine of pi is -1. That's the minimum value for cosine. So -1 times -4 is +4. So I just kind of used what I knew about sine and cosine. So I'm well studied on my unit circle. Which you're like, ugh. It's okay. All right. 27th derivative of cosine. Well, if we say that y is equal to cosine, actually let's do f of x. I don't want to draw 27 primes, right? That seems excessive. The first derivative is negative sine. The second derivative is going to be negative cosine, right? The negative sign is like a coefficient, right? So we ignored it. The third derivative is positive sine. And the fourth derivative is back to positive cosine. Notice that we've just completed a cycle. So what I'm looking at here is the 24th derivative. What's that got to be then? Yeah, just going to be cosine again. So the 27th derivative should be the same as the third derivative. So it should just be sine. Done. Mr. Kulik, I thought that was going to be like unbelievably tedious. It could have been. You could have done it, just kept differentiating and done that 27 times. It's not absurd. It's pretty annoying though. I'm going to assume that there's a shortcut if somebody's asking you to do 27 derivatives, right? It's like Mr. Kulik's never asked us to do something that dumb before. Elena. Certainly. All right. Just a couple more. What does this kind of look like? What does this limit kind of look like?
Sine over the.
Yeah, it kind of looks like this one, right? That's what I'm going to make it turn into then. That's going to be my goal. Okay? So which one is going to be possible for me to do? Can I make this sine x over 7x, or can I make it sine 4x over 4x?
The first one.
The first one is right. So how am I going to change that 4x into a 7x? You mean 4 over 7, but yes. Oh, shoot. I can't just, yeah, so, okay. So I just, let's just do this. Okay. So I can't do that by itself, right? But I can do that, right? Okay. My apologies. Why do I need that extra 7/4 on there? Because I'm just multiplying by 1 then, right? Now I haven't done anything at all. So I'm just going to cross off the part that I need. And everything that's left over just is going to I'm going to stick out front because it doesn't depend on x. And what is this part going to be? Just 1. That wasn't so bad, right? Emma. Yeah, I chose to multiply by 4 over 7. That'll cancel out the 4's and leave me with a 7x down in the denominator. But if I did it, I can't just multiply by that, because now I'm changing the value of this fraction. I also have to multiply by its reciprocal, so I'm doing like nothing at all. So the first fraction cancels out what I need to. The second fraction is there, so it's basically canceling the first fraction, right? So it's doing nothing. Just makes it look the way I want it to look. I know, I'm excited too. What's up? Oh, okay. Am I being named after the paper man? Or is the paper man being named after me? Okay. I'm honored. Until you rip him in half after class or something. You'll leave it for X. Okay. All right. What are we going to do with this thing? That is a really good question, Emma says. X cotangent X. Great. So Rita's suggesting cotangent is just cosine over sine. So we can do that. But the identity that I'm going to be looking to use is going to be,
Cosine minus 1 over.
nope,
What we just did.
still going to be using this one.
How do you know that it would be that one?
Because I see that there is no adding or subtracting in this. And I see I have both I have a fraction, I have a cosine, or I'm sorry, I have a sine and I have an x. Right? So basically I have x over sine instead of sine over x. You see that? So I just have to come up with a clever way to write that so I have sine over x instead of x over sine. Anybody with that clever idea of how to do this? So again, right now I see x over sine. I need it to look like sine over x. What's the reciprocal of a reciprocal?
1, 1.
That's like doing nothing at all, right?
Yeah.
So this is the way I'm going to write it. I'm going to write it like a complex fraction. Because when I divide the two fractions, I multiply by the reciprocal, right? Sneaky. So what can I do now? Well, I can use my limit laws and take the limit of the top over limit of the bottom. And I know this is okay to do because what's the limit of the bottom? Not 0, right? It's 1. What's cosine of 0? It's 1. So there we're done. Again, sneakies, the sneakers, did some sneaking. But that's it for this section 3.3. Again, majority of what you're doing in this is going to just be practice using these new derivative rules for sine, cosine, tangent, secant, cosecant, cotangent. So your bold problems are 7, 11 through 15 odd, 23, 33, and 37. And that's not until next week, too. May I make a suggestion for you guys?
Yes.
Over this basically 1 week until I see you again, try to take a little bit of time and memorize your derivative rules that we've gotten so far. Okay? This class will feel a lot easier and the lectures will go a lot better if you're on the same memorization page as I am, where like when we say things, you're like, yep, okay, that is what that is. I know it because I've spent the time memorizing it, and it's just like everything will flow a little bit easier and it won't feel like as much catch up. So like product rule, quotient rule, your power rules, your sum difference, constant multiple, like all those derivative rules to this point, like get those things down like 100% where it's instant or instantaneous, and things will feel a little bit easier since you have a week and one homework assignment to worry about, and I don't think this one is particularly even that difficult. Maybe those are famous last words, Mr. Kulik. They're all difficult for me. I know. But I think that'll make a big difference. Emma? Yeah, so 11, 13, and 15, yes. Of course. Because the next section or next derivative rule we learn, I don't think it's a hard one, but it can make it allows me to make some really complicated problems. Okay, so yes. So what you're gonna see is, like, when we did the quotient rule, you really only could get one quotient rule in a problem, right? When we did the product rule, you could kind of only get like one or two product rules reasonably in a problem, right? But with the chain rule, you can do like, oh, there's a chain inside of a chain, inside of a quotient with a product, and like you can get like really tricky in terms of like, okay, what order am I really applying these things? When are they happening? And that's the part that's hard. The rule itself is simple. It's just the derivative of the outside times the derivative of the inside. But when you have like, okay, the derivative of the outside's a product property, or I'm doing a product property and one of the derivatives is a composition, so I have to do that. And inside of that, the thing inside of it's like a quotient rule. So it's like,
Interesting.
you can get a lot of, what's up? I don't have a Sharpie, it ran out of ink.
Dang it.
I have a highlighter.
Yeah.
Will that work?
I'm trying to write on my notebook,
Yeah, no.
like on it.
Yeah.
It's okay.
I have this as kind of like an icing pen.
It's okay.
I don't have a Sharpie right now. It ran out of ink last week. I went to get it out to use it, and I'm like, well, that's not helpful. So anyways, the point I'm trying to make is, with the chain rule, it's going to be really advantageous that you have the rest of these rules like memorized stone cold and can recognize that like, oh, okay, I need to start this with a product rule, and when I do this derivative, there's a chain in there, and when I do this inside of the chain, that's a product, and when I do that product, there's like another chain in there. So it's just easier to see them if you're like, instantaneously recognizing them. And it's like, oh, and this was like a square root inside of a trig function, inside of a fraction. Like you can see where this gets like, oh, this is going to be kind of a lot. The good news is after the chain rule, that's really as complicated as things get for derivatives. So it's like, we get there, and then we do some, there's one more set of rules for logarithms, but they're not complicated, and can be really helpful. And then some more application stuff. But this is going to be a short trip to the test because 3/8's kind of a nothing chapter. In fact, look at my notes for 3/8. I don't even think we're going to do it. 3/10 is super easy. Like, that's it. It's basically writing tangent lines. 3/7 is just like story problems. Look at what I have written down for my 3/7 notes so far. Just like one example problem. So be ready that it's going to go quick once we get past implicit differentiation, which is, what do you do if you have an x and y on the same side? Like unseparable. Like y is no longer just a constant or a variable by itself. It's like a function in its own, but, and we have the inverse trig functions that come in there that we need to learn the derivative rules for too.
Okay, I totally forgot about explanation.
Why?
Or the stuff inside